R equals I divided by T equals in the first room, one customer every 15 seconds. That is a completely legitimate R if you want. Okay, so the R there is flow units per period of time. So if you want to do the flow unit as a customer, and you want your period of time in seconds, that is completely legitimate. R is 1/15 of a customer per second. I don't want to work in fractions, okay? I like to work in kind of nice whole numbers. Usually on the exams, I'll suggest units to use, but you can do whatever you want. I'm going to go ahead and I'm going to convert this to customers per hour. That sounds something useful to me. It could be customers per day, customers per whatever. I'm going to go ahead and do it in customers per hour. How do you do that? Well, remember, you got to get seconds in the numerator over here to cancel that second, and then you have to have hours here. So we need to know how many seconds are there in an hour. And we know there are 3,600 seconds in 1 hour, and then we'll end up finding out what that is in terms of customers per hour instead of customers per second. Everybody clear with that? Another way to do it is 15 seconds, that's 4 in a minute, that's 240 in an hour, right? Okay, so this is 240 customers per hour. Okay. And now, I'm not going to go through all that detail for all the rest of them because I think we can do it. So we're just going to do it in our head real quick as we go through it. And we're just filling out the nameplate for each of these cubicles. By the way, the nameplate on the blue room is going to be the exact same thing as in the cubicle because there's only one cubicle at the present moment per room. So we can go ahead and fill this out too. This is one customer as possible in that room at a time. Once a customer leaves that triangle and enters that room, that customer will leave in 15 seconds, and the flow rate is 240 customers per hour. There's no problem with having the denominator of the rate different time units than the time. As long as you're consistent with all the T's and consistent with all the R's, that's fine. So you get R into whatever time unit makes sense to you, you get T into whatever time unit makes sense to you. Everybody cool with that? All right, so if we do the rest of it very quickly, this one is 30 seconds. I equals one customer. That's 2 a minute or 120 an hour, right? 120 customers per hour. All right, for number 3 equals 60 seconds. I equals one customer. That's 1 a minute or 60 customers per hour. Okay, T of this one is 40 seconds. That's 1.5 per minute, 90 per hour. All right, number 5, the time is 20 seconds. That's 3 a minute or 180 per hour. And then the final one, T equals 30 seconds. There's one customer. All right, that's 2 a minute or 120 customers per hour. Now, for completeness, let's go ahead and fill the blue rooms because I'm about to add something and then the rooms will be different than the black. So let's go ahead and fill in the blue rooms. So it's just repeating what's here. Because this box says what's happening in this room. But if we look inside, there's only the one cubicle in the room, so the same thing's happening.
So basically the green is the addition of all
The green is the behavior of the everything that's happening in the green box. Yeah. I notice how I did not agree with your statement, it's the addition, okay? So the green is what's happening in the entire thing. Okay? You're about, this will all become clear. Just give me a sec and it'll all become clear, okay? Now, I was very deliberate in avoiding the triangles when I drew the blue rooms, okay? Because by avoiding the triangles in the blue rooms, a room contains only boxes. So whatever I measured for the box is the same thing I measured for the room. So from a room perspective, this is all pretty easy. I could walk up, I can look on the nameplate, and I say, okay, here's what's going on in that room. If I poke my head inside the room, I see there's only one cubicle and I have the same nameplate. But do you see how I'm a little screwed when it comes to the green one?
Yes.
All right, so the problem with the green one is the green one contains both triangles and rectangles. And until I know what to do about those triangles up there, I'm kind of screwed. I really can't answer the question yet. I cannot answer the question yet what time is, and I really can't answer the question yet what I is. Because I would be 1 plus 1 plus 1 plus 1 plus 1 plus 1. There's 6. But how many are in those triangles? I don't know. So, right, I don't know exactly what's happening in the triangles, so I don't know what I is. Same way with T. If there were nobody in the triangles, it'd be 15, 30, 60, 40, 20, 30. That would be T, but I don't know how long they're having to spend in the triangles. So I'm a little bit, I can't do much with that. In fact, the only thing I really can do is I can remember that T, remember there was this theoretical flow time plus the weight. So I can answer what the theoretical flow time is, because the theoretical flow time is what if I never had to wait? I don't have to spend any time in triangles, right? The theoretical flow time is 15 plus 30 plus 60 plus 40 plus 20 plus 30, okay? So basically, that's the theoretical flow time plus the weight. So basically, I know that T is going to be equal to 195 seconds for the theoretical flow time, but then I need to figure out what the weight is. So that's all I can answer right now. All right, last question for you. And all of this is the questions on the next page, by the way. I'm just answering all these questions, okay? So, draw the process. I did. Where's the bottleneck? Now let's think about that. Okay. If hang on, y'all are doing great, but y'all are ruining my story, okay? So here, all right, I want to come over here, and I want to stand, and remember, I forgot who asked, but the question was whether is it flowing in or flowing out or whatever. So let's go stand here. Let's stand at the exit, and let's look at the rate at which customers are leaving this process. That's pretty easy, right? I just look, and it looks like this last room is 120 customers an hour. So do you agree that 120 customers an hour are coming out of the door?
No.
Why not?
Because 120 aren't getting to number 6.
Okay, so it's all wonderful and great and good that workstation number 6 could do 120. The only problem is workstation number 3, you gotta go through that room can only do 30, so it doesn't matter that those can do faster than 60. The fact of the matter is we can't go any faster than 60 because it is the bottleneck, right? That's the idea. So we got the bottleneck. By the way, the bottleneck is because R is the lowest, not because T is the longest. In this case, the longest T is also the lowest R. That will not be the case in about 5 minutes, okay? All right, so don't go looking at the T's. The T's are a means to an end. It is the R that defines the bottleneck. The lowest flow rate through here is the 60 that room number 3 is going to do. Okay? Everybody clear? So now we can go, oh, well, we at least can talk about the R of the process is the R of the bottleneck. The R of the bottleneck is R of workstation number 3. So basically, we can at least say that the flow rate of this process is 60 customers an hour. The fastest anyone can ever get through this process is 195 seconds, but I don't know how long it's actually taking them because I don't know what's happening in the triangles. So far, so good. So we got the first one. Draw the process as a simple serial flow line. We got the next one. Where's the bottleneck? It's workstation number 3. We got the next one. What's the maximum process flow rate? It's 60 because that's the bottleneck. What's the theoretical flow time? Well, the theoretical flow time is 195 seconds, right? And then I said I was going to give you a way to calculate labor utilization. So let's think about this for a minute. In fact, let's draw a little picture of people here, okay? Just so we keep in mind you know, that there's one worker in here. So there's one worker in here. Here's the little worker person. Here's another worker person. There's only one worker person in each of these cubicles right now. Again, on your homework, we're gonna relax this. There's gonna be more than one station. There may be more or less than one worker for each of these things. So right now, we're just setting up for the simplest case what happens. And I'd like to know, what is my labor utilization? So here, I'm gonna make a verbal argument and then try to show you why this is correct. Let's start with this one over here. Maybe I'll kind of do this. Okay? I'd like to know how busy I'm keeping that person right now. Do you agree that if we were able to, we can't, but if we were able to run this room as fast as it possibly could, right? This room would be doing 120 customers per hour, correct? And at 120 customers an hour, that person is as fully busy as they're going to be, correct? But how many are we actually running through that room? So how busy are we keeping that person? Half of what they could, right? So that's what we're gonna do. We're gonna go ahead and we're gonna create a weighted average. And I'm starting at the end because there's a reason why I have to start at the end, and then just bear with me. So I'm gonna say, for that last room in there, I'm gonna say there's one person in that room, okay? And that person is working at, well, the bottleneck is limiting that person to 60, but that room is capable of doing 120. So I'm gonna say that's the weight, that's the utilization of that one person in that last room right there. You agree? Okay. Now let's back up. And let's look at the preceding one. Do you agree the same argument can be made?
Yes.
This room could do 180. How many is it actually doing? 60. So how busy am I keeping that one person?
33%.
That's right. So there's one person in there. The bottleneck is limiting me to 60. That room could do 180. Now let's back up again and just keep on with the same process. There's one person in the fourth room. The bottleneck is keeping us to 60. That room could do 90. So there's that weight of that person. Then we get to the bottleneck. There's one person in that room, right? It's only running 60 through it, but it can only do 60. So the resources in that room are running as busy as they can, correct? Okay? Here's why I went backwards. We gotta figure out what we're gonna put in this room. Okay? And here's the temptation. The temptation is, suppose you were the manager of room number 2 here, and you were evaluated on utilization. Wouldn't you try to run your room as fast as you possibly could? All the way up to 120 customers an hour, provided that we could get enough customers in here, right? So I would want to run this sucker as close to 120 customers an hour as I could, correct? And my utilization could then get all the way up to 100% if I were doing it. Can't do that after the bottleneck because the bottleneck's starving us, so we don't have anything to work on. But potentially I could do that before the bottleneck, correct? What's the problem with that?
Increase the time.
You didn't accomplish diddly shit when you did that, okay? You didn't. Why?
You increase the.
I want you to imagine a speedometer. I want you to imagine a speedometer on this room right here, okay? And the speedometer can go all the way down to 0, all the way up to the max of 120, okay? But remember, we're not just trying to make this room look good, we're trying to make the green box work better, aren't we?
Right.
All right, so I start turning up the speedometer on that room, it's at 0. How much is getting through the green room right now if that's at 0? Nothing's getting through, right? So I start turning up the speed. It's 0, it's 10, it's 20, 30, 40, 50, 60. All the way up until I get to 60, there is a 1-to-1 improvement between how fast I'm running that room and what the flow rate in the green room is, right? And there's no penalty. I'm not hurting anything as I run faster, correct? Now, I take it, I go, hey, I've been doing great. I went from 0 up to 60 and everything's looking better and I'm getting raises and everything. Well shit, I'm gonna run to 65. So I turn it up to 65. Let's look and see what happens when I turn it up to 65. Did any more get out down here?
No.
Nothing more got out, right? Did anything bad happen when I turned it up to 65?
Yeah.
Yeah, he just started pumping stuff into here faster than the rest of the system can handle, right? So didn't you just increase waiting time? Didn't you just decrease the flow time efficiency when you did that? So there's no point in running that room any faster than the bottleneck allows it to run. Why would you ever run any room faster than the bottleneck allows it to run? Because if you're evaluated on the proxy measure called utilization, you're rewarded for utilization even if it actually harms the overall system. That is exactly what was happening in TI. All of the section area managers were evaluated on the utilization that they were keeping their equipment running. So what would you do if you were doing that? You'd allow a bunch of shit to batch up in front of you, right? And then that would allow you to keep on running all the time full speed, so you'd look really good. But the problem is you get into the whole problem we just described with the TI thing. It's a problem of a proxy measure. It's not because of bad people. It's because if you measure me on utilization, I'm gonna give you utilization. But there's no point in this room of any higher than 60. So I'm gonna calculate the effective utilization, not the fake utilization, the effective utilization. I'm gonna say there's one person in that room really shouldn't run any faster than 60 because it doesn't accomplish anything, and that room is capable of doing 120. And I'm gonna do the last thing with the first one, and it's exactly the same answer. Yeah, I might have shit tons of customers waiting out there to come through here, and I can look good by pumping them through, but we have the same problem we just talked about, don't we? Okay, so there's one person here that is capable of doing 240, but it makes no sense to go any faster than 60. Now we're doing a weighted average. This is the weight of the first room, here's the weight of the second room, and so forth. And the right to get a weighted average, you have to divide by the weights. Okay? That's how you can calculate labor utilization. If you like it in equation form, okay? There it is in equation form. Just summing up for each of the rooms, I, going from 1 to however many there are, it's how many workers are in that room, times what is the bottleneck rate flowing through that room, divided by what is that room capable of doing. And then you can divide by the total number of workers. Now I wrote it that way because later on we're gonna have, what if I told you it took 3 people working to keep this room running? Well, then there's gonna be 3 people in there working, whatever that utilization is. Yeah? What if one of them's fully automated right here? Doesn't matter that the room is only running at 60 out of 90. There's no workers in there, so it doesn't have any impact on utilization. It'd be 0 times whatever that is. So this will work. That equation will always work, and it allows us to calculate the labor utilization. In fact, we can calculate whatever utilization you want. I don't know, maybe there's a fancy computer in here and a fancy computer in here, and you want to know how well you're utilizing computers. Well, there's no fancy computer in here, so that'd be 0 times 60 over 240, so it would have no impact on that, right? Maybe there's one fancy computer in here, it'd be 1 times 60 over 120, and so forth. You follow? So we're just going to follow that kind of thing anytime we want to calculate this. Now let's make it a little harder.
What is the I number?
I is just a counter. Here's workstation I number 1, I number 2, I number 3, and so forth, okay? So let's make it a little harder, because right now, there was a lot of redundancy there. So let me tell you a story, and then let's make it a little harder. First of all,